PyTorch. What is PyTorch? It's a framework to help you do deep learning. Now, where were you the first time you heard about deep learning? I'll tell you where I was. I was riding an elevator with a couple of coworkers, and one of them turned to me and started asking all these questions about deep learning and how it's going to change everything and how it's better than what came before. The guy didn't know much about machine learning, so I told him, nah, don't worry about that deep learning stuff. It's just a fad. Boo! Boy, was I wrong. So anyway, after 3 months of kind of like with my head in the sand like that, I started to realize that unless I figured out what deep learning was and quick, they were going to come and strip me of my PhD and send me back to like the kiddie pool because deep learning is the wave of the future. So some of the advantages of PyTorch are that it's just kind of really easy to use. It lets you set up a neural network without having to know a lot of what's going on under the covers, but you can always learn that stuff later. And then it does most of the math stuff that you'd have to do to learn a neural network for you. It's very flexible. For a long time, it was the #2 neural network framework behind TensorFlow, but I think recently PyTorch has picked up a lot of momentum and it may be the #1 framework right now. So it's a great thing to invest a little bit of time in and figure out what it is by going through a tutorial like this one and building your first neural networks with it. Here are the steps for building a neural network with PyTorch. #1, you got to load data. #2, you got to get the data into the right format for PyTorch, like load it into PyTorch's data structures. #3, you have to set up the neural network that you want to learn and some components around it, like the loss function that you're going to use and the optimizer. And we'll get into details on what those things are. #4, you're going to do the backpropagation algorithm using PyTorch, and I'll show you the loop that does backpropagation. It's not too much code, and I'll explain what the elements do. Then #5, you're going to want to test the model that you produce to see if it's any good. I always say that in machine learning, evaluation is creation. And what I mean by that is that until you've tested something and until you know what it is, it's nothing at all. Let's get into the code. I will put the code online so you can follow along. I'll also put a link to the data set. If you don't have PyTorch installed, I'll also link a video that tells you how to get going with that. So here's the beginning of the code. And this is really the first 2 steps that I talked about in the overview. That is loading the data into RAM and getting the data into PyTorch's data structures. So let's just start with where we're trying to get to. The PyTorch data structure is called a tensor. So each training example needs to be loaded into a tensor, and each label needs to be loaded into a tensor. We're going to try to have parallel arrays so that the training data index 0 and the label index 0 correspond to the same training example. So that's where we're trying to get to. Where we're starting from is a directory full of images. The particular problem that I'm going to use for this sample is an eye blink detector. That is, it takes an image and it predicts whether that image is of an open eye or of a closed eye. These 2 steps need to go from a directory of images on the disk to a bunch of tensors that PyTorch can work with. Let's go through how to do that. Now, this first step, I've hidden some of the details because this is just raw Python. What this Python does is it goes to the directory that contains the images and iterates through this directory hierarchy to produce a list of paths and labels for training data and for testing data. So it's simple, os.listdir stuff. And if you don't know how to do that, I recommend you go and watch a Python tutorial and then come back and finish up this PyTorch tutorial because, this level of Python coding is sort of a prerequisite to working with PyTorch. So this is what the data looks like. There's a directory for closed left eyes and closed right eyes. So those would get the label closed, every image in those directories. And there's a directory for open left eyes and open right eyes. So any image in those would get the label of open. So the Python code just iterates through those images and collects lists of the paths so that we can work with them later. So the next step is to take these lists of paths to image files and load those files into memory. To do that, you use a library called PIL, Python Image Library, and you just iterate over the training paths and the testing paths and call open on them. And then that produces these arrays of images. So that's all it takes to load the data into RAM. Okay, now we need to get these images into tensors so that PyTorch can work with them. And a tensor is essentially just an array of floating point values. So in the image, each image is 24 by 24, and each pixel is represented by a single byte, so 0 to 255. So we want to turn that into a bunch of arrays of floats between 0 and 255 in the tensor data structure so that PyTorch can work with it. And so to do this, we can use these library functions that PyTorch provides. And we essentially iterate over the images and call transform to tensor on each image in turn. And this transform will convert, extract the data from that image data structure and convert it into a floating point array like we need. And then we use another torch function called stack, which stacks all the different images together into a single array. When this code is done running, you can, at the console, run get the train tensor and ask for its size. And you'll see that it's 24 by 24 is the innermost element, which is the 2 by 2 image. Each image is wrapped in a tensor. And then there are 3,877, which is the size of the training set. We're done with the data, and now it's on to some fun stuff. We're going to start in the modeling. We're going to start looking at the learning algorithm. But before I do that, I want to spend a little time going over concepts. Now, I'm not going to explain this stuff in detail. I'll link to a lecture where I talk about neural networks in excruciating detail for something like 90 minutes. But right now, I'm just going to give 5 or 10 minutes of the basics of the concepts so that when you see the code that implements learning, you'll have a little bit better understanding of what it does and why that code is the right code. Neural network is a model that takes observations, passes it through a network of artificial neurons. Each neuron activates based on what it sees in its inputs, and all of the neurons lead towards an output from the network, which is the prediction of what we're trying to do. So in this case, we have a 24 by 24 image as our input. So our neuron, when we get to the code, will have 24 by 24 inputs. Those will flow through the network to produce the output. In this sample right here, I just have 2 inputs, x1 and x2. So you can see the concepts. But when we're doing the code, just keep in mind that there's a lot more inputs than just these 2. So right here, there is a input sample that has 2 inputs, x1 equals 1, x2 equals 0.5, and a correct label of y equals to 1. Inside the network, there is going to be these artificial neurons, like I said. So in this case, neuron number 1 takes inputs x1 and x2, and neuron number 2 also takes inputs x1 and x2. That is, they both get to look at the full input. Each of these neurons, based on some properties of them, which we'll discuss in a little bit, look at the input and produce an output signal, which is called the activation. And those feed deeper and deeper into the network. In our tutorial today, we're going to have a very simple network that has inputs, a single hidden layer, and a single output layer. But in general, this architecture will be much, much more complicated. State-of-the-art models have something like 4 million parameters within them, whereas this network that we're going to be learning today has more like 10 parameters in it. So these things can get quite big and quite complicated. Then in this network, neuron number 3, which is the output neuron, examines the activation of these 2 hidden neurons and uses them to produce the output from the network. Y hat, the hat typically means a prediction from the example, not the actual label. And that's how that works. So here's the code that creates the neural network that we want to learn. But we need to specify to PyTorch that it has this particular structure of a single hidden layer and a single output layer and how everything relates to each other. So for the next few slides, I'm going to go through how we do that. To create a network structure, you need to subclass from a torch class. In this case, it's torch.neuralnetwork.module. So we create a subclass of that, and that subclass creates all the neural network objects and links them together internally. Once we've done that linking in our code, then Torch can use those linkages to train the model and to use the model in practice. So now we're going to go through how you show Torch what linkages to use in your neural network. There's a init method, and that takes in whatever parameters we want. In this case, I've decided to input the number of hidden nodes to use as a parameter. So there's still going to be one layer, but you can control the number of hidden nodes in that layer. In the example, there were 2. In the code, there will be 5. In order to create the network that I showed on that previous conceptual slide, we need to stack 2 PyTorch primitives together. The first primitive is a linear layer, and the second primitive is a sigmoid activation function. So we stack those together using this wrapper called torch NN sequential. The linear layer maps from the inputs to the hidden nodes. So in this sense, we have 24 by 24 inputs, and that's the size of each image. Remember, it's a 24 by 24 by single byte per pixel. And then hidden nodes is the parameter that we've passed in. So this maps from every pixel in the image to the 5 nodes and makes a connection between each pixel and each hidden node. The sigmoid function is a way to add non-linearity into the neural network. And that's a very important concept to enable a neural network to model and represent complicated concepts. It's a little bit subtle. I'm not going to go through too many details. Suffice to say that a sigmoid function has the property that it maps an infinite range from negative infinity to positive infinity into the range of 0 to 1. So if the input to a sigmoid is 0, the output is 0.5. If the input is super positive, the output gets closer and closer to 1, but never quite reaches 1. And the same thing on the negative side, it never quite reaches 0. In that sense, it's a great way to add nonlinearity, but also to convert the activation of a node into a 0 to 1 range, which we can interpret as a probability. And here we produce the output layer from the network that I showed on the previous slide. Again, we stack a linear layer and a sigmoid activation. And this time, the linear layer maps from the hidden nodes, however many we specified, to the single output that we want to have from the network. So now we've specified the structure of the network we want to build, but we have to tell PyTorch a little bit more. And that is, we have to tell PyTorch how to use that structure to make predictions. And the activity of taking an input and mapping it through a network to get a prediction is called forward propagation. Now this slide gives a sample of forward propagation. We have the same input, the same 3-node network, but here I've also indicated the weights that each node has. And these weights determine how much a node activates for any given input. In particular, the activation of neuron 1 is going to equal this math right here. And I'm sorry for showing a little bit of math. About 90% of the people I show math to roll their eyes back and they're like, oh, you're killing me with the math. Oh, I'm going to die. And about 10% of the people say, you got to show me all the math. If I don't know all the math, I don't understand this. Please give me more math, more math, more math. So your mileage may vary, but I just want to give you a really quick breakdown of how forward propagation works, one level deeper than what you need to know to do PyTorch. So in order to get the activation of node 1, remember we had a linear model wrapped in a sigmoid. And so that's what's expressed right here. And that linear model takes input x1, multiplies it by weight 1, which is a parameter on the node, adds that to input 2 times weight 2, which is another parameter on the node. And then there's a bias weight, which is always 1, or the input is always 1, and this weight there is multiplied by the bias. And that allows the linear model to be expressive and express any plane in the hyperdimensional space that you're in, blah, 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 blah. Then this value is summed up and it's passed through the sigmoid function, which converts it to a value from 0 to 1. So each activation here is going to be a value 0 to 1. The same thing will happen on node 2. And the same thing again will happen on node 3, where this time, instead of taking x1 and x2 as input and multiplying it by their weights, the node 3 takes the activation 1 and the activation 2 as inputs and multiplies them by the weights that are stored on node 3. And all of that just produces the output, which is the prediction of the network for this particular sample. Okay, now that we understand the forward propagation concept a little bit, we can finish creating our neural network template. Remember, we did the structure here, and now we have to tell PyTorch how to do forward propagation with this structure. So to do that, you say, well, if you give me an X, I will first convert it from being a 2 by 2 array to being a 1 by n array, because we're not using 2 by 2 operators. You could certainly do 2 by 2 operators and specify some of them up here. Those are things like convolutions, but we're not doing that for this sample. So the first thing we need to do is convert it into a one-dimensional data piece. Then we take that one-dimensional data and we pass it into fully connected 1, which is the layer we specified there. Then we take the output of that first layer and pass that into the output layer, which is the layer we specified there. And then that out there will be the y hat that we return from the function. So this is how we tell PyTorch to do forward propagation. And it's also how we draw too many lines on a graph. Okay, so that's what this code does now, and you can now interpret what's going on here. And so we've created a model which has the right structure in it and has the ability to do forward propagation. The next thing we need to do is talk about the loss function. And there's a lot of options here. I'm just going to go through a very quick concept of what it means to have a loss function and what the point of a loss function is. Okay, so here's the neural network where we've just completed forward propagation. Remember, we got y hat equals to 0.82, and somehow we really wanted to get a 1. And what loss is the difference between what we wanted to get and what we did get out of the network. There's a lot of ways you could think of loss. Probably the most simple would be to do something like MSE, which stands for mean squared error. And so on a particular sample, you would take the value that you wanted to predict, subtract the value you did predict, and square that difference, and then sum that over all samples and take the average to get to the mean squared error. That's a very standard thing to do. With neural networks, another very standard thing to do is slightly more complicated. It's called binary cross entropy, or sometimes it might be called log loss. And here it's just a little bit more math, but it has very similar properties to the mean squared error. It just penalizes different sizes of errors differently. You know, the trade-off between making a lot of small errors and making a few large errors is just different with binary cross entropy. Anyway, when you're doing machine learning with neural networks, you're going to have to specify a loss function. You're probably going to want to tune it based on the properties of the problem you're working with. There's a lot to learn. Right now, we'll stick with binary cross entropy. So the way that works is the loss is y, comma y hat. In this case, we plug in the values 1 and 0.82, call binary cross entropy on those values, and we get back 0.086. And so that is, in essence, how hard the training algorithm will want to work to fix this example. So the next time it sees the inputs of 1 and 0.5, it would work harder to predict 1 instead of predicting 0.82. And that's what the loss function says. Okay, let's take a little breather right here. Stop, relax, and think. What we have is data loaded into memory, moved into tensors, which are the PyTorch data structure. We've created the neural network structure we want to learn, and we've defined loss, which is how hard the algorithm should work to correct any particular mistake that it makes. Higher loss, more work to correct it. Now I'm going to tell you a little bit about the learning algorithm and how these elements come together to create the backpropagation algorithm. Backpropagation algorithm has a number of steps. The first thing you do is you take the training data and you do forward propagation for every sample in the training data. Here I'm demonstrating a single example like I've been showing you before. The next thing you do is you calculate the loss. So you figure out how much each training sample is adding to the overall loss. The next thing you do is called backpropagation, which is you want to figure out how much each node in the network is responsible for the loss that you have for that training sample. So one way to think about it is that the output layer makes the final decision. It does its best to predict the example. It's made a mistake. A lot of that mistake is because of what the output layer did, but the output layer has to propagate that mistake back and say, hey, these other nodes were telling me something crazy. I made a mistake, but it's really partially their fault. And so the backpropagation algorithm is how do you figure out how much of that mistake goes to each of the nodes that contributed to it. One kind of simple way to think about it is that if node 2 had a larger activation than node 1, then node 2 would be more responsible for the mistake. Also, another big element of it is that if node 3 had a higher weight that it used to multiply activation 2 than the weight it used to multiply activation 1, then node 2 would get more of the blame for that particular loss. So anyway, there's a whole algorithm behind it, and I think this is the concept, and this is really what you need to know. But basically, the step 3 is to take that loss, propagate it through the network, and for each node, figure out how much of the blame for that loss is that node accountable for. Then the final step of the backpropagation algorithm is to update the weights. So every weight in the network that contributed to that loss multiplied by the amount of blame that that node had for that mistake. And there are a lot of ways you could take that step. In our Hello World example that we're doing here, we're just using the Torch Optimizer SGD. And SGD stands for Stochastic Gradient Descent. And so what that means is that all of this backpropagation, you calculate what's known as the gradient, which is the direction to change the weights to most decrease the loss. So you calculate that using the backpropagation algorithm, then you do gradient descent. And so what that means is you take a step proportional to your learning rate in the direction of the gradient. And that means you update every weight in the network by a small step amount in the direction that most lowers the loss. One nice thing about PyTorch is that once you've specified the network structure and how you're doing forward propagation and which optimizer you want to use, you just link them up. And here's how the linkage happens. You tell the optimizer, here are the parameters I want you to try to improve. And it's going to figure out how to do all of this stuff that we talked about on this slide. All of this is completely transparent to you. And I just wanted to show you this so that you have a sense of what's going on behind the scenes when we start to talk about the code that does this part in detail. Great. Now we've got everything set up and you have all the basic concepts that you need to understand why this code is going to learn a neural network that can tell if an eye is open or an eye is closed. Let's dig in. So to train the model, some bookkeeping, because you always want to know how long you're sitting around. This line right here takes your model and applies it to the training data. And what is that? Forward propagation. So it gets out the prediction. So there's all the y-hats for every example in the training set. This step here calls the loss function that we decided to use. Remember, that's binary cross entropy. And it takes the predictions that the model just produced and compares them to the correct labels. And it produces a loss data structure, which contains all the information about the loss that happened throughout the network. The next step is that you have to go to your optimizer and say, zero yourself out. You can put this call at different places in the loop, but basically you want to say, set all those blames for the loss back to zero, because we're about to do it again. And this call to loss backwards sets all the gradients in the network so that the optimizer knows which direction to take a step in. Then you just simply call optimizer step, and that will take a step based on the learning rate we specified in the direction that the loss indicates we should go to most improve the neural network at the prediction task we're trying to train it on. There you go. Pretty simple stuff. A few bookkeeping elements. When we're printing this out, the loss data structure, you have this function called loss.item, and that converts it back from kind of tensor space or GPU space into something that you can print out. So that's just a little trick you need to be aware of. The other thing is that you would basically never write this training code. I just said, do 2,500 iterations of this backpropagation algorithm. In reality, you would have some holdout set, and you'd be testing as you go to figure out when the model has converged and when you should stop running this loop. That's all it is. Now we have the model trained. Now we got to ask ourselves, is it any good? Was it any good? Can we stop? Do we need to do more work? I don't know. The first step is to say that the model is no longer in training mode. That shouldn't matter for a very simple neural network, but it's a good habit to get into because as you start to use more advanced structures, the model will behave subtly differently at training time and evaluation time. So you really do need to get in the habit of using that code. So what we do is we apply the model that has had its weights updated by all of that training to be the best weights possible. We apply it to the test data. We get out the predictions, and then it's just some simple Python code to calculate from those predictions what our overall accuracy is. So here's what it looks like when I ran this program in my console. Bunch of iterations scrolled off the top of the screen. I was printing the loss. It went down for a while, then it stopped going down, something like a convergence there. When training was complete, the time was about 6.7 seconds. Turns out a lot of that time was spent printing all this stuff out on the console. So later when I give timing results, they'll be a little bit different than that. And the final accuracy was 57%. Not great, but this is a very simple model, single hidden layer with 5 neurons in it. Shouldn't have really expected it to be too great. Well, there you have it. That is the code for training a neural network with PyTorch, some of the concepts behind it. Let me give a quick summary. So here's what we have. We have a computer. There's the disk, the RAM, and the CPU. Step 1 is to load the data, which is get it off of the disk into the RAM. Step 2 is convert it into the PyTorch data structures of tensors. Step 3 is to set up for modeling, where we create the model structure, we pick the loss function, and we create the optimizer. Step 4 is to do backpropagation until convergence. And then step 5, of course, is to test. But we're not going to stop there. One of the big enablers of the power of deep learning has been training on graphics cards or GPUs. And there's really one big reason for this. It's that the GPU is a parallel processing unit that's just about perfectly set up to do the types of operations that you need to do in a neural network for forward propagation and backwards propagation. And not only the weight multiplications during those processes, but the ability to do multiple training samples simultaneously through the same network. It just allows GPUs to be much, much faster than CPUs, and it's been a real enabler. So if you want to get into doing deep learning, you're going to have to get an NVIDIA graphics card. You're going to have to go install CUDA drivers. Again, I have a link to some information about how to do that. And you're going to need to modify your code from the version I showed you up until this point to the version I'm going to show you next, so that you do your training on the GPU instead of on the CPU. So conceptually, these are the changes we need to make. Instead of doing backpropagation as step 4, we move that to step 5. And step 4 is we transfer all the data and all the models onto the GPU. So we have to move those things into RAM on the GPU, and then we do the backpropagation on the GPU, create the model there, and transfer it out of the GPU to do the testing that we need to do or to use it later on. So small change, just one step, and PyTorch makes it pretty easy. Let's look at the code. So this is the code we saw before that created the tensors that we needed for PyTorch to be able to learn. And here's the code to move the tensors to the GPU. This first thing is a little convenience. You can set up a device that is CUDA, which means GPU, if CUDA is available, which means you installed it correctly and you're on a machine where it's enabled and installed and all of that stuff. But if you're not on such a machine, default back to the CPU. So this code will all work perfectly fine whether or not you have CUDA available, but it'll just be a lot slower if you don't have CUDA available. So print that out. And then here is the code. You just say, hey, tensor, go to the device that you're going to train on. So this will make a copy on whatever the device happens to be. You know, I wrote GPU here because I know on my machine I have a GPU, but if device happened to be CPU, you would now have 2 copies on the CPU. That's fine. You don't have to worry about it. So you just move all the tensors that you're going to want to work with onto this device, hopefully your GPU, and you're pretty much good to go. The next step is that when you're creating the model, you have to do this one extra step, which is say model to device. And so basically I overwrite the model with a copy of the model on whatever device that we're doing the training on. Everything else stays the same. Now we have the model on the GPU, the tensors on the GPU, and here's the backprop code. One small change you need to make is reference the data on the GPU, or the correct version of the model, the correct version of the data tensors. The other thing you need to know is that these intermediate results are now sitting in GPU RAM, like this loss thing, these Y-train predicted. So that's why another reason you need to call loss.item. So there's just some little helper functions that transfer information between the GPU and the CPU so you can observe them and et cetera, et cetera. Okay, so here's the run of the GPU-enabled code. I took out all those console prints, which were taking so much time. So the time here was 3.7 seconds, and the accuracy was 64%. Contrast that to a version of the CPU run where the time is 4.9 seconds, and the accuracy is 59%. So there's two things to see here. Number one is that, taking out all the console output, even on such a simple toy problem, using the GPU is 26% faster. Now, if you had much larger training data, many more parameters in your model, this difference would grow much, much larger than 26%, and it would be a total enabler. Also, you'll see in later videos, if you continue watching this series, that training a model and tuning it to be actually excellent requires many, 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 many training runs. So every little bit helps. You may end up doing hundreds or thousands of training runs. So if you're talking about, 10 days of model training in order to do the tuning that you need, 26% faster is actually like 2.5 days. So it's very meaningful. Another thing to notice here is that the GPU run seems to be a lot more accurate, but I'll tell you, it really isn't. This is the type of variance that happens because of the weight initialization. When you create a model, all the weights in the model are randomly initialized to small values. And depending on how that initialization goes, the training process can get stuck in local optima. That's one of the reasons I just said you have to do so many runs to create a good model, so you can make sure you're not getting stuck in a problem like this. So to summarize with that, using the GPU doesn't magically make things more accurate, but it allows you to learn on bigger problems with larger models, do more runs in your tuning, and end up with more accuracy through that process. Okay, great. Moving to the GPU wasn't so bad. Just a few lines of code to change, and we're good to go. Now we can build all sorts of crazy deep neural network models. Unfortunately, that's not the case, because the approach that we used is only going to work well with very small toy problems. And as you start to get into real applications, we're going to hit some snags. Let me walk you through why. Here are some of the benchmark datasets that have been used with recent deep neural network breakthroughs. Don't need to go through them, but you can see that there are tens to hundreds of gigabytes of data. So right there, your brain's got to be going, boop, how are we going to make that work? It gets even a little bit worse in that you'll often do what's called data augmentation, which is take the input data and add some stuff to it. In the case of our eye application, you might flip the eyes so a left eye looks like a right eye and vice versa. That's a pretty safe way to get more training data that's going to help you avoid those local optimums we were talking about earlier. So to get a little bit more concrete, this data is from Steam, which talks about gaming PCs and how much RAM they have available. You're watching an intro to PyTorch video, me and you right here, right now. That means you're probably not working at some top deep neural network training lab. You probably don't have access to ludicrous machines. So let's assume that you have a machine that's similar to a typical gamer's machine right now. Well, you probably have 16 gigabytes of RAM on your machine or 8 gigabytes of RAM on your machine. Or maybe if you're getting into machine learning, you've bought a little bit extra RAM and you're up to 64 gigabytes of RAM. But even that is not enough for a lot of these data sets, so we hit a snag there. Another problem that we'll have when we're pushing the limits on the GPU is the size of our model. The one that we've been using through this Hello World PyTorch project has 10 parameters in it. It's like something like 40 kilobytes. State-of-the-art in computer vision has 4 million parameters. That's a lot bigger. And NLP can be bigger still. These things are only going to get larger. And what it comes down to is that you really can't fit the data you want to train on and the model you want to train into the GPU's RAM at the same time. So you're going to have to do something about it. Just for completeness, here are the statistics on GPU RAM on gamer machines. And most kind of high-end gamer cards have 6 or 8 gigabytes of RAM now. So that's probably what you're working with. This stuff up here is typically the server GPU cards, and those cost a heck of a lot more. So unless you're willing to spend thousands of dollars on a really fancy GPU, you're going to be in the 6 to 8 gigabyte range. And even spending all that money on the fancy GPU doesn't get you a heck of a lot further. So what are we going to do? Let me show you the concepts of what we're going to have to change in order to get out of the toy problem world and start making progress on real problems. The first thing we need is a data iterator. And this is a combination of two PyTorch concepts. One of them is a data set, which you will create by subclassing from the PyTorch data set to have all the properties of the data that you need. And the other is a data loader, which will use the data set to batch data onto the GPU so you can do training one little bite-sized chunk at a time. So you set up the data iterator and you load data from the disk into it, or that's the data set, and load data from the disk into it. Here you can do all the tensor stuff. You can do caching, you can do transformations. We'll get into that in a little bit more detail. You set up for modeling the same way we did before, where you load the model and move it over to the graphics card. Now, if you're trying to train a very, very large model, you may have multiple graphics cards. You'll certainly have to do something tricky on that part of the problem. For this tutorial, we're going to assume that your model can fit on the GPU and it's the data that you're having problems with. The next thing you're going to do is iterate these steps. You're going to use the data loader to load a small batch of the data into RAM, move it to the GPU, and then you're going to do backpropagation on the GPU with that subset of the training data. So you're going to make an update to your model's parameters on just a small portion of the data, not on the whole data. And then you're going to just keep going, sending the next chunk of data and the next chunk of data and the next chunk of data, and calculating all the losses and backpropagating to calculate the gradients and everything you're going to need to do. But you just do it one bite-sized chunk at a time. Little bit of vocabulary, let me reiterate. A batch is the subset of training data that you can fit onto the GPU. And so you'll go batch by batch by batch through your data set. And an epoch is what happens when you've gone through all the batches that make up your data set and you've essentially done one complete pass through your data. Remember the previous versions of the program, it was 2,500 passes of backprop. And so that would be 2,500 epochs, which would be broken up into a bunch of batches depending on the size of the batch you use, depending on how much of the data you can fit onto the GPU at one time. So a few points here. You may need to chunk the data from your disk into CPU RAM. If you don't have enough CPU RAM to load the whole data set at once, your data set class might need to deal with that and load data incrementally. Another thing is that you can augment the data before you hand it to the GPU. So you can hand the same bit of data augmented a few different ways before having to move on to the next data. I mean, the sky's the limit. Those types of decisions about what to do are more advanced topics. For now, I'm just going to show you the basics. Okay, when we're working with this data iterator, the dataset and data loader, there's one thing you need to do. The data loader class will fork the process and create child processes. So if you don't put this if name blah, blah, blah stuff there, everything's going to crash and it's not going to be good. So this is just to help the data loader do what it does. It's a minor change that you have to make to your program. You can load the raw data the same way. So we get the file paths and the labels. But now the question is, what are we going to do with those file paths? When are we going to load the images into RAM? When are we going to convert them to tensors? And that's what this iDataset class does. The iDataset takes the paths and the labels, and we have one for the training data and one for the testing data. Now let's click into this and see what that code looks like. So what this code does is it takes all that stuff about loading the images, converting to tensors, et cetera, et cetera, et cetera, and puts it into a class. Remember, the init method takes the files and the labels, stores them in members, and then caches all the images in another member. So now we've created a CPU RAM cache of all the images. Then the next step is we produce all the tensors from those images. So essentially everything we did before, because the data set fit on the CPU, we just do it all into CPU memory. Then we put it into this data set class, and then the data loader, which we'll see in a second, is going to be able to use these methods to get the data, put it into batches, and move it to the GPU. So a quick summary: cache of the images in CPU RAM, cache the tensors in CPU RAM, and then just return the cache data to build the batches that we're going to transfer to the GPU. This is one way to do it when you have plenty of CPU RAM, your data set isn't too large. Another thing that you might have to look into is not caching at all. And of course, you'll almost certainly use some hybrid between the previous version and the version that we show here. So this version is the same in that it takes the paths and the labels, but now it just specifies a compound transform object. So previously, we've just been using this transforms to tensor. In this example, I'm showing data augmentation where I'm doing random horizontal flips. Remember, taking the left eye and making it look like a right eye or vice versa. So this transform object does two things at once. It augments the data and converts it into tensors. We cache the label tensors because those are going to be pretty darn small. The problem will be the images. And then whenever the data loader asks for an item, we do all the work to load the image data into CPU RAM, augment it and convert it into tensors, and then return those tensors. But this could be pretty slow because instead of reading each image file from disk once, we read each image file from disk once per epoch. So if you get into this type of situation, you bump into these kind of fun systems challenges of how do you use threads and consumers and producers and hide all the stalls of waiting for the data to come from the disk. You might not find that as much fun as I do. But anyway, there it is. So in summary here, we have a transform that augments and converts images to tensors, and then we load and process each image every time it's used. The data loader is the PyTorch class that takes the data set and deals with everything for you. It lets you specify how large you want your batches to be. You can shuffle data or not shuffle data. You can specify how to do parallelism and a whole bunch of other stuff. I'll show how to use this in detail on the next slide. For now, just like to say there's one bummer if you're a Windows user. If you set number of workers to anything other than 0, your app is going to go crazy slow and it just doesn't work. Essentially, the parallelism on Windows that PyTorch does just takes about 4 to 5 seconds per thread that it starts up. And so it's totally not acceptable. So if you really need to scale up, you're going to have to use Linux and you're going to have to set num workers to something other than 0, something related to the number of CPU processors you have. What I'm really hoping is that somebody who's watched this video will be like, no, Jeff, you're wrong. Actually, blah, 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 and tell me how to get parallelism working on Windows so I don't have to mess with Linux quite so much. Please leave a comment if that happens. And here's the code to do batched backpropagation. We still have the for each epoch. We start off by zeroing out the gradients because for each batch, we're going to add more and more and more to the gradients. And then at the end of going through every batch, we're going to take one step. So we use the dataset generator to create the batches. We move them to the GPU. We do the forward propagation. We do the loss calculation. We do the back propagation, and we iterate across all the batches, just adding up more and more loss on the gradients in the model. And then after we've gone through every batch in the epoch, we do one step of the optimizer. So that's not so bad. I mean, it's a little bit of code in the data iterator, the data set that you have to write, but it's not crazy. And here we go, the output of this run. You can see I've turned the console output back on, so it's printing out the epochs. And the training run completed in 75 seconds this time. So much, much slower than doing everything in parallel all at once. But like I said before, if you're going to work with very large data sets, you're going to need to do this type of batching. And a lot of the work that you do will be figuring out how to cache appropriately, how to set the right batch size, how to trade off model parameters versus your GPU RAM to achieve the best results. That kind of stuff's actually really fun to me. So it's an interesting time to be involved in doing machine learning. So that's it. Tutorial done. We went through the hello world of PyTorch. We talked about how to do things on a GPU and how to scale up past toy problems to some degree. Now remember, if you want to learn more, this is video 2 in a 5-video series, how to install hello world, making more complicated network structures, doing modeling end-to-end for something like a Kaggle competition, and then really almost intermediate level model tuning with PyTorch. So please go check those out. I also have links to videos that explain all the concepts that I've talked about here in much more detail, and I'll link those below as well. Hey, thanks for watching. Good luck.